In this lecture, we're going to continue our discussion of quadratic functions. We're going to look at some word problems where the model is quadratic, but rather than stopping with just the model as we have in the past, now we're going to answer some follow-up question using our knowledge of quadratic functions, and in particular, what we've learned about finding the vertex of a parabola. Let's start with an example that we've already set up once. A farmer wishes to enclose a rectangular field with 1,500 yards of fencing. What dimension should she choose to maximize the enclosed area? If we want to do this problem algebraically, our first job is to find a function that models the situation. We want to come up with an equation that represents the scenario. Well, we've done this previously. In a prior lecture, we did this problem. A farmer wishes to enclose a rectangular field with 1,500 yards of fencing. Express the enclosed area of the field as a function of the width of the enclosure. So we said the area was the length times the width. We used the fact that the perimeter of the fence would be 1,500 yards to solve for L. We made a substitution, and we rewrote the area as a function of the width. And you'll notice that that function is quadratic. It's a polynomial function of degree 2. Let's steal that function and use it to answer our question. We're trying to find the dimensions that should be chosen in order to maximize the enclosed area. Well, the area function was quadratic, 750w minus w squared. Let me rewrite this so that the quadratic term is first. That's the negation of w squared plus 750w. This is a quadratic function where the input is one of the dimensions of the enclosed region, and the output is the area of that region. Well, we know that the graph of this quadratic function will be a parabola which opens downward. And the input that will maximize the enclosed area is the first coordinate of the vertex. We have a formula for finding the first coordinate of the vertex. We take the opposite of the coefficient of the linear term and divide by 2 times the coefficient of the quadratic term. We said that it was opposite of b over 2a. So the width that maximizes the area is the opposite of 750 divided by 2 times negative 1. The coefficient on w squared here is negative 1. Simplifying that, that's the opposite of 750 divided by negative 2, which is positive 375. The width that we want is 375. Does that answer the question? No, not quite, because it wants to know the dimensions that should be used. We have the width, we also need the length. The length we said is 750 minus w. So the length that maximizes area is 750 minus the width that maximizes area. Well, that happens to also be 375. Those of you with good geometric intuition might have guessed that the way that you're going to maximize the area of this rectangular field is to make it a square, to make the two dimensions the same. That's bared out by our math. The width and the length that maximize the area are both 375. The units on both of these are yards. The problem did not ask for the actual maximum enclosable area, but if we wanted to find that, we would have two options. We could plug 375 in for w in this function to find the output. You would just plug in the input. Or keeping in mind that area is length times width, we could just multiply 375 by 375 and get the area that way. Let's do another example where we already have the function. Sometimes in a textbook problem, they just give you the function, you just have to work with it. A ball is thrown vertically upward with a velocity of 100 feet per second. If the release point of the throw is 6 feet above the ground, then the height h of the ball after t seconds is given by the function h of t equals negative 16t squared plus 100t plus 6. How high is the ball at its peak? So you don't have to know where this function comes from. You might if you've done some physics, but you don't have to know where it came from. They gave us the function. Somebody's throwing the ball at 100 feet per second. To get a feel for that, that's just under 70 miles per hour. The release point of the throw is about 6 feet above the ground, and you can use this function to model how high the ball is after t seconds. We're looking for the maximum output of this height function. Well, the height function is a parabola, and it opens downward because the leading coefficient is negative. The maximum output of the height function occurs at the vertex, so we're once again dealing with the vertex. The question is, which coordinate do we want? Do we want the input or the output? The question is, how high did the ball go at its peak? So we're looking for the height, which is the output. Let me transfer this function onto another slide. In order to figure out how many seconds it takes to reach its maximum height, we do opposite of b over 2a. That's the opposite of 100 divided by 2 times negative 16. That's the negation of 100 divided by negative 32. That reduces to 25 divided by 8, which is 3.125. So it takes 3.125 seconds for the ball to reach its maximum height. That's not the question, though. The question is, how high is the ball at its peak? How do we figure out the max height? Well, we plug the time that we just found into the height function. We're going to evaluate h of 3.125, or h of 25/8, which is the equivalent fraction. So this is negative 16 times 3.125 squared, plus 100 times 3.125, plus 6. Throwing this into a calculator, I get 162.25. That answer is in feet. So the ball reaches a maximum height of 162.25 feet. I want you to notice that I did not round the input. If I had rounded this to 3, that's not going to give me the maximum attainable height because I'm stopping short of the peak. You can't round this if you want to find the actual maximum. We would get a good approximation, but you won't get the exact answer unless you use the exact input. So those first two examples aren't so bad because we either already set up the function before or we were given the function in the problem. These get a little more difficult when you have to come up with the model yourself. So in our remaining examples, we're going to come up with the function ourselves. Let's start with a classical kind of example, which just looks kind of like a math trivia question. It says, prove that if two real numbers have a sum of 200, then their product cannot exceed 10,000. How would we do this? Well, we need variables, and I think the most common variables here would be x and y. We're trying to find the max value of x times y subject to a constraint, subject to the constraint that x plus y must be 200. Now, how are we going to do that? Well, if we could rewrite this as a function of a single variable, and it turns out that that function is quadratic, then we know how to find the maximum output of the function. So how could we rewrite this so that it doesn't have two different variables in it? That's where our constraint comes in. We know that the two numbers have to add up to 200. The sum of the two numbers has to be 200. I can solve that for either of the two variables. Let me start with x plus y equals 200 and solve it for y. I'm going to subtract x from both sides. So I get y equals 200 minus x. Now I can make a substitution. I'm going to call the function p for product. The product was originally x times y. I'm going to write that as a function of x only by substituting 200 minus x in for y. This is now a function of only x, so I can write this as p of x. If I multiply this out, I get 200x minus x squared, or rewriting it in descending order, I get negative x squared plus 200x. I do that just to make sure it's clear which coefficient is a and which coefficient is b. You don't actually have to do that rewrite. We're trying to find the maximum output of this function. The output of this function is the product. How do we find the maximum output of this function? Well, first we find the input that maximizes the output, which is the x-coordinate of the vertex. And then we plug that in to get the maximum possible output. So the x value we're looking for is the opposite of 200 divided by 2 times negative 1. And that's the opposite of 200 divided by negative 2. That's 100. Now we plug 100 into the function. So we get the opposite of 100 squared. I put the parentheses there to make sure it's clear that we're squaring the 100, not negative 100. Plus 200 times 100. 100 squared is 10,000. The negation of that is negative 10,000. 200 times 100 is 20,000. And the sum of those two terms is 10,000. The maximum possible product is 10,000. Therefore, the product cannot exceed 10,000 because that's the max. Problems like that are a good warm-up. Those aren't the ones that most people are worried about. It's usually the ones that have some sort of story. So let's do a couple of those. A citrus grower estimates that if 50 trees are planted, the average yield will be 350 oranges per tree. The average yield should decrease by 5 oranges for each additional tree planted. How many additional trees should be planted to maximize the total number of oranges? So you can probably guess what our strategy is going to be. We're going to write a function that represents the scenario. We want the input to be the number of additional trees. We want the output to be the total number of oranges, and we're going to try to maximize that function. When we pick our variable here, you might be tempted to use O for oranges, but that might look like a 0. So let's just be boring and use X. We're going to let X be the number of additional trees. And we're looking for the total number of oranges. I'm going to be boring and pick Y. The Y kind of makes sense anyway because it's the total yield. Now we need to set up a function where Y is written as a function of X. So first we're going to start with a word equation. How would we figure out the total number of oranges? That's what we want to know. Well, let's go back to the grower's estimate and see if you can figure it out in that specific situation, and then we'll just generalize. The grower estimates that if 50 trees are planted, the average yield will be 350 oranges per tree. So how would you figure out the total number of oranges? If you know how many trees there are and you know the average, how do you figure out the total? You multiply them, right? You take the average number of oranges per tree times the number of trees, that'll give you the total number of oranges. Let's write that out as a word equation. It's the average yield times the number of trees. Let's write this in symbols. We said the total number of oranges is going to be denoted by Y. What is the average yield? Well, if they planted 50 trees, it would be 350. But they're thinking about planting additional trees. And for each additional tree planted, you're going to lose 5 oranges per tree. The average decreases by 5. See if you can put that together. I'm going to repeat it when I switch slides. If 50 trees were planted, you'd get 350 oranges per tree. But for each extra tree you plant on top of those 50, you're going to lose 5 oranges per additional tree. See if you can write that expression. We're starting with 350 oranges per tree, but we're going to lose 5 for each extra tree. Remember, X is the number of additional trees planted. So for example, if they plant 51 trees, that's 1 tree above the 50 that they're talking about in the scenario, in the estimate. We should lose 5 oranges from that, so it should be 350 minus 5, that's 345, and that's exactly what you get when you plug 1 into this factor. It seems like this factor works for the average yield per tree. Now we need an expression for the number of trees. I think this one will be a little bit easier. In the estimate, we're assuming they'll plant 50 trees. But we're going to increase that by X trees. See if you can come up with an expression for the number of trees if we're starting with 50 and increasing that by X. Yeah, that one's a little bit easier. That's 50 plus X. Again, if they were planting 51 trees, then X would be 1. We would multiply that by the 345 oranges per tree, and that would be the total yield. The goal wasn't to stop with the function. The goal is to figure out how many additional trees should be planted to maximize the total number of oranges. We want the value of X that maximizes this function. And there is a way to do that without multiplying it out, but we haven't talked about that. So we're going to have to use the FOIL process to multiply this out. 350 times 50 is 17,500. 350 times X is 350X. Negative 5X times 50 is negative 250X. And negative 5X times X is negative 5X squared. I'm going to rewrite this in standard order from highest power of X to lowest power of X. So we get negative 5X squared plus 100X plus 17,500. Again, the goal is to figure out how many additional trees should be planted. That's the X variable. So we just need the X coordinate of the vertex. The number of additional trees to max the yield is the opposite of B divided by 2 times A. That's the negation of 100 divided by negative 10. That comes out to 10. So they should plant 10 extra trees for a total of 60. Let's try one more. A real estate company owns 218 efficiency apartments which are fully occupied when the rent is $940 per month. The company estimates that for each $25 increase in rent, 5 apartments will become unoccupied. What rent should be charged so that the company will receive the maximum monthly revenue? So again, we need variables here, and notice that this time we're not asking about an increase or decrease, it says what rent. So I'm going to use X to represent the rent. And we're trying to maximize the monthly revenue. It's common to use R for revenue. Let's start with a word equation reminder here. The revenue that you generate is the amount of money that you bring in. You don't worry about any costs. The amount of money that this real estate company brings in on these efficiency apartments is the rent that they charge per month times the number of occupied apartments. They only get paid on the apartments that they rent out, the ones that are occupied. So we're going to multiply the number of occupied apartments by the amount of rent that those people pay. We want to rewrite this in symbols. We want to write R as a function of X, where X is the rent. Well, that makes the first part of this easy. The rent is just X. The hard part is going to be coming up with the number of occupied apartments. And I'm going to show you an organized way to do this. You can kind of do this by intuition. You could write it out just by using your intuition, but I want to show you a process to do this. Notice what it says here. For each $25 increase in rent, 5 apartments will become unoccupied. That is a linear relationship between the rent and the number of occupied apartments. So I'm going to come up with the equation of that line. And how do we usually come up with the equation of a line? We come up with 2 points on that line. So we're going to come up with some ordered pairs. The first coordinate in each ordered pair is going to be the rent. And the second coordinate in each ordered pair is going to be the number of occupied apartments. So we're still using rent as X, and we're calling the number of occupied apartments Y. We're given one specific scenario. All of the apartments are occupied when the rent is $940 per month. When the rent is $940, rent goes first, the number of occupied apartments is 218. That information is given. The company estimates that for each $25 increase in rent, 5 apartments will become unoccupied. So if we increase that rent by $25 to $965, they're going to lose 5 customers. They're going to have 5 apartments unoccupied. They're going to be down to 213 occupied apartments. I can use this to model the number of occupied apartments for any given rent. First, I find the slope. The slope is 213 minus 218 over 965 minus 940. That's negative 5 over 25, which is negative 1/5. Now I can use point slope form. Y minus the y coordinate of either point, I'm going to use the first point arbitrarily, equals the slope, negative 1/5, times x minus the x coordinate of the same point. X represents the rent, y represents the number of occupied apartments. We are trying to come up with an expression for the number of occupied apartments, so I want to solve this for y. And I would do this by multiplying out the right side first. This is negative 1/5 x plus, let's see, 1/5 of 940 would be 188. Changes to a plus sign because a negative times a negative is a positive. We add 218 to both sides, and we get y equals negative 1/5 x plus 406. This is the number of occupied apartments in terms of the rent. We can use this expression to represent the number of occupied apartments in our revenue function. This is negative 1/5 x plus 406. Now I distribute, that's negative 1/5 x squared plus 406x. And now let's see if we can remember what the problem was asking us to do. What rent should be charged so that the company will receive the maximum monthly revenue? We're trying to find the rent that maximizes the revenue function. The rent is the x-coordinate, so we're looking for the x-coordinate of the vertex. So the rent that maximizes revenue is the opposite of b over 2a. Let me write that down here because of the fraction. That's the opposite of 406 divided by 2 times negative 1/5. That's the opposite of 406 divided by negative 2/5. Remember that when you divide by a fraction, it's like multiplying by its reciprocal. So this is like negative 406 times negative 5/2. 2 goes into 406 203 times. 203 times 5 is 1015. A negative times a negative is a positive. And so it turns out that they'll maximize their revenue by charging $1,015. They will lose some customers because of that. They'll have some unoccupied apartments. But the increase in price makes up for that up to a certain point. If they increase the price too far above that, they lose too many customers and it'll actually drive the revenue down. The spot that will maximize their income is $1,015, not taking into account any costs. We're only looking at revenue here. Problems like this definitely take practice. I encourage you to seek out a textbook and do a bunch of problems of this type. As many as you can find. If you have any questions about how I approached any of these problems or follow-up questions, for example, I mentioned that we could have found the number of occupied apartments without using this organized process. You can kind of do it by intuition. I'd be happy to walk you through that. Just shoot me an email, see me in an office hour, we can talk it through.